September 14th, 2023, Bakersfield, California. The salvage reports from modern locomotive restoration specialists would never fully capture what they witnessed that morning. American mechanics standing before a first-generation diesel locomotive that had sat motionless for 40 years, using diagnostic equipment that confirmed what every contemporary engineering principle said was mechanically impossible. Through the dust and morning heat of the abandoned Southern Pacific siding, an EMD GP7 diesel locomotive rested beneath 4 decades of rust and bird nests. No climate control, no preservation treatments, no maintenance schedules honored. Yet its electrical systems showed continuity that modern locomotives could not match after just 5 years of storage. In contemporary rail yards, diesel mechanics required complete engine rebuilds after locomotives sat idle for more than 18 months. Each unit was essentially custom restoration. Different seals, different injectors, different electrical harnesses. Most carried failure rates far beyond what railroads could economically justify. The Americans were looking at engineering durability that modern manufacturers had declared commercially obsolete. EMD 567 engine block, mechanical fuel injection, generator-based electrical architecture, component redundancy, triple contemporary standards, operational lifespan that reduced replacement cycles from years to decades while supporting unprecedented runtime hours. 3,000 miles from modern locomotive factories, the most decisive diesel engineering philosophy in railroad history was revealing itself. Not in computerized engine management, not in lightweight composite materials, but in the systematic overbuilding techniques that connected every American component in ways modern efficiency optimization never imagined necessary. The inspection crew from Pacific Harbor Line arrived at the forgotten industrial siding with equipment designed to document complete mechanical failure. Among the rust-streaked hulks crowded onto the weed-choked trackage, restoration supervisor Michael Chen carried a diagnostic tablet while junior mechanics wheeled battery carts across cracked concrete. Every abandoned locomotive brought the same depressing arithmetic: seized pistons, corroded wiring, fuel systems transformed into sludge reservoirs. Standing before Unit 2487's weathered nose, Chen studied the locomotive's faded Southern Pacific markings with the calculating assessment of a 42-year-old mechanic who had spent 2 decades declaring first-generation diesels economically impossible to restore. The GP7's paint had oxidized to bare metal in patches, its cooling fans frozen solid with accumulated debris, and its air reservoirs certainly ruptured from decades of freeze-thaw cycles. The technical challenges seemed insurmountable to every restoration specialist except the railroad historians who remembered these locomotives' original specifications. Built in 1952 at UD, General Motors' Electromotive Division Unit 2487 represented peak American diesel engineering, before cost optimization became the industry's driving philosophy. Its 567 cubic inch displacement engine produced 1,500 horsepower through 16 cylinders of two-stroke diesel combustion, generating torque characteristics that modern high-speed engines could never replicate for heavy freight service. Most daunting of all, the sheer age required systems ancient enough that replacement parts existed only in specialized museums, while the electrical architecture predated transistors, microprocessors, and every electronic control system that contemporary locomotives depended upon for basic operation. Modern locomotive orthodoxy had crystallized around one immutable principle since the computerization revolution of the 1980s. Diesel engines older than 15 years were economically dead, regardless of their mechanical condition. Electronic fuel injection, microprocessor controls, and emissions regulations had rendered first-generation diesels legally inoperable across most American railroads. Railroad maintenance directors concluded that GP7 restoration was financially impossible. The parts supply chains had collapsed decades earlier. Mechanical fuel injection systems offered none of the precision that modern common rail systems delivered, while generator-based electrical architecture consumed 30% more fuel than modern alternator designs during equivalent operations. Yet Chen's inspection checklist contained observations that contradicted 4 decades of railroad industry consensus. His secret lay not in modern replacement components, which every contemporary restoration attempted, but in evaluating the original 1952 engineering exactly as EMD's wartime trained designers had specified it. The GP7's durability emerged from World War II. Locomotive production philosophy. General Motors had built diesel engines for landing ship tanks that operated in saltwater environments, survived beach landings, and ran continuously for months without specialized maintenance. Those marine engines taught EMD engineers that simplicity trumped sophistication when reliability mattered more than efficiency. The mathematics were elegant in their brutality. Mechanical systems with zero electronic dependencies created exponentially greater storage durability than computerized engines that failed when their circuit boards corroded. Unit 2487's fuel injection system used spring-loaded plungers activated by camshaft rotation. No sensors, no processors, no electrical dependencies whatsoever. Chen's initial visual inspection revealed what modern engineers had forgotten to consider. The GP7's engine compartment showed no evidence of water intrusion despite 40 years of weather exposure. EMD's designers had sealed the locomotive using gasket technology and drainage systems developed for Navy vessels, creating weather protection that modern cost-optimized manufacturing had abandoned in favor of cheaper assembly methods. Opening the engine access panels required portable angle grinders to cut through seized latches, their mechanisms frozen solid from decades without lubrication. Yet inside the compartment, the full engine block showed minimal surface corrosion. Its cast iron construction had oxidized into a protective patina rather than destructive rust, while the cylinder liners retained their original honing marks beneath accumulated dust. The electrical cabinet told an equally surprising story. Modern locomotives used printed circuit boards that degraded rapidly in humid environments, their solder joints corroding and their semiconductor components failing from moisture exposure. Unit 2487's electrical system employed brass bus bars, ceramic insulators, and electromagnetic relays built to specifications that prioritized durability over miniaturization. Each electrical connection used mechanical fasteners rather than soldered joints, creating systems that could be disassembled and serviced using basic hand tools. The main generator itself weighed 4,800 pounds, triple the mass of equivalent modern alternators, but its copper windings showed no signs of the insulation breakdown that destroyed contemporary electrical machines after extended storage. Chen's team spent 3 days documenting systems that existed nowhere in modern locomotive manuals. The air brake system used all metal components rather than the rubber diaphragms that modern units employed, creating pneumatic controls that could survive indefinitely without preventive maintenance. The fuel tanks were welded steel rather than the aluminum alloys that contemporary locomotives used, showing no signs of the stress cracking that plagued newer designs. Modern diesel mechanics arrived expecting comprehensive failure, their diagnostic equipment calibrated for contemporary locomotives that measured engine parameters through dozens of electronic sensors. Unit 2487 offered none of these monitoring points. Its engine operated through pure mechanical principles that predated the sensor technology that modern railroads considered essential for safe operation. Lead mechanic Robert Torres connected a portable battery bank to the locomotive's electrical system, expecting nothing more than documenting dead circuits for the restoration estimate. The ammeter registered 128 volts across the main bus, impossible for batteries that hadn't been charged since 1983, yet the reading held steady without fluctuation. The GP7's battery compartment contained 8 individual cells connected in series, each one a massive lead-acid unit weighing 245 pounds. Modern locomotives used sealed gel batteries that lasted 5 years maximum before requiring replacement. Unit 2487's batteries were open-cell designs that mechanics could service by adding distilled water, a maintenance procedure so obsolete that Torres had never actually performed it during his entire career. Checking the battery, electrolyte levels revealed the first genuine surprise of the inspection. 7 of the 8 cells contained crystallized sulfate deposits that made them unusable, exactly as modern theory predicted, but the 8th cell maintained a liquid electrolyte that tested at 1.240 specific gravity, essentially factory-fresh condition despite 40 years of abandonment. The single functional cell couldn't power the locomotive's electrical systems, but it demonstrated something that contemporary battery technology never achieved: the ability to maintain charge indefinitely through sheer overbuilding of component materials. Modern batteries self-discharge within months of installation. This 1952 lead-acid cell had retained electrical potential for 4 decades. Torres moved to the engine inspection with professional pessimism earned through years of failed restoration attempts. First-generation diesel engines used wet-sleeve cylinder liners that corroded rapidly when exposed to condensation, creating bore damage that required complete engine replacement. He removed the inspection covers, expecting to find cylinder walls pitted beyond salvage. The cylinder bores showed crosshatch honing marks. Original factory machining from 1952 preserved beneath a microscopic oil film that EMD's lubrication system had deposited during the locomotive's final operational moments in 1983. Modern engines used dry sleeve cylinders with chrome plating that prevented oil retention, creating surfaces that corroded within months of storage. Unit 2487's wet sleeve design had created its own preservation system. The oil film prevented oxygen contact with the steel surfaces, while the sleeve design allowed moisture drainage rather than accumulation. The engineering philosophy was obsolete by contemporary standards, yet it had achieved what modern technology could not: 40 years of perfect preservation through purely passive systems. The fuel injection pumps presented the next impossible scenario. Modern common rail systems used precision machining tolerances measured in microns, with moving parts that seized solid if exposed to contaminated fuel. Unit 2487's mechanical injectors operated on principles adapted from Detroit Diesel's World War II. Two engines, using spring-loaded plungers with tolerances measured in thousandths of an inch rather than millionths. Torres removed the first injector, expecting to find its plunger frozen in place by oxidized fuel residue. The plunger moved freely under finger pressure, its surface showing no signs of corrosion or deposit buildup. The mechanical simplicity that modern engineers dismissed as primitive had created a fuel system immune to the degradation that destroyed contemporary injectors after minimal storage periods. October 3, 2023. Chen's crew had spent 3 weeks servicing systems that shouldn't have required servicing, changing fluids that hadn't degraded, replacing gaskets that hadn't failed, cleaning filters that had somehow remained functional. The restoration budget projected $340,000 in parts alone. Actual expenditures totaled $8,200, primarily for new batteries and fresh diesel fuel. Modern locomotive startups required computer diagnostics to verify hundreds of sensor readings before attempting engine ignition. Unit 2487's startup procedure came from a 1952 operations manual. Confirm air pressure, prime fuel system, engage starter motor, monitor oil pressure. 4 steps that assumed the locomotive's mechanical systems would function exactly as designed, without electronic verification. The air compressor represented the first genuine test. Modern units used electric motors driving aluminum pump heads, creating compressed air through high-speed rotary mechanisms. The GP7's compressor was a 2-cylinder reciprocating design driven directly from the engine's accessory drive, built to operate at slow speeds with maximum durability rather than efficiency. Chen engaged the auxiliary starter motor that powered the compressor independently of the main engine. The compressor's drive shaft turned grudgingly for 3 rotations, then suddenly broke free as decades of congealed grease liquefied under friction heat. Within 90 seconds, the air pressure gauge climbed from 0 to 90 psi. Main reservoir full, exactly matching the 1952 specification despite 4 decades of inactivity. The fuel priming procedure required manual pumps to fill the injection lines before attempting engine start. Modern locomotives performed this process electronically, using computer-controlled pumps that precisely metered fuel flow. Unit 2487's fuel system operated through mechanical advantage, long-handle pumps that physically forced diesel through the lines using nothing more sophisticated than check valves and spring pressure. 30 strokes on the priming pump produced resistance indicating fuel had reached the injectors. Torres opened each cylinder's test cock, small valves that allowed mechanics to verify fuel delivery manually, and confirm diesel spray from all 16 cylinders. The procedure was obsolete, dangerous by contemporary safety standards, yet it provided absolute confirmation that the fuel system functioned without requiring diagnostic computers. Chen positioned himself at the engineer's controls while Torres stood by the engine compartment's emergency fuel cutoff. The starting procedure required holding the starter button for exactly 15 seconds while monitoring oil pressure gauge response. Modern engines cranked at 300 RPM during start attempts. The GP7 starter motor turned the massive engine at barely 60 RPM, each compression stroke audible as individual piston movements, rather than the continuous rotation contemporary mechanics expected. 5 seconds. The engine turned over with mechanical precision, each cylinder firing in sequence without the electronic timing systems modern engines required. 10 seconds. Exhaust smoke appeared from the stack, black carbon. Deposits from 40-year-old injector tips, clearing as fresh diesel displaced ancient residue. 15 seconds. The oil pressure gauge flickered, then jumped to +PSI as the mechanical pump established lubrication flow throughout the engine block. Chen released the starter button. The 567 engine continued running at 3,000 RPM idle speed, its exhaust note settling into the characteristic EMD two-stroke rhythm that had disappeared from American railroads a generation earlier. Unit 2487 was running under its own power after 16,000 days of absolute silence. The running engine revealed truths that modern locomotive design had systematically eliminated in pursuit of efficiency optimization. Unit 2487's 567 engine operated at mechanical speeds that contemporary high-performance diesels would consider catastrophically slow. Maximum governed speed 835 RPM. Modern freight engines operated at 1,050 RPM minimum, generating equivalent horsepower through increased cylinder pressure and turbocharging rather than displacement volume. The GP7's design philosophy emerged from radically different priorities. EMD's engineers in 1952 built locomotives expecting 50-year operational lifespans, designing every component for unlimited rebuilds rather than planned replacement. The crankshaft alone weighed 400 pounds, solid forged steel machined to tolerances that allowed mechanics to regrind bearing surfaces 6 times before requiring replacement. Modern crankshafts used lighter alloys and tighter tolerances that reduced weight by 40% while eliminating rebuild capability entirely. Contemporary engines were designed for 2,000-hour service lives before complete replacement, creating planned obsolescence that Unit 2487's designers would have considered engineering malpractice. Chen's diagnostic tests measured parameters that modern locomotives monitored electronically every microsecond. Cylinder compression, PSI average across all 16 cylinders, varying by less than TSA despite 40 years of storage. Modern engines showed 10% compression variation when new, with degradation accelerating rapidly during service life. The combustion chambers told their own story. Torres removed cylinder heads expecting carbon buildup that would require chemical cleaning. The piston crowns showed carbon deposits measuring barely 0.042 inches thick. Negligible accumulation from decades of operation followed by decades of storage. Modern engines developed similar carbon deposits within 5,000 operational hours, requiring frequent cleaning to maintain efficiency. The metallurgical secret lay in EMD's material specifications. The 567 engine used cast iron cylinder heads rather than the aluminum alloys that modern engines employed. Cast iron operated at lower temperatures, reducing thermal stress while creating combustion surfaces that naturally resisted carbon adhesion. The engineering trade-off sacrificed weight efficiency for unlimited durability. The electrical system demonstrated a similar overbuilding philosophy. Modern locomotives used solid-state voltage regulators weighing 8 pounds and costing $12,000 to replace when they failed. Unit 2487's voltage regulator was a 140-pound electromagnetic device using carbon pile resistors and mechanical contactors, technology that predated transistors but could be rebuilt indefinitely using basic electrical components. The generator itself represented engineering philosophy that modern manufacturers had completely abandoned. Its rotor assembly used copper bars silver soldered into slots, creating electrical conductors that could handle sustained overload conditions without damage. Modern alternators used aluminum conductors that weighed less but failed catastrophically when overloaded, requiring complete unit replacement rather than repair. Chen measured the generator's electrical output, 1,420 kilowatts at rated engine speed, matching factory specifications within 2% despite 4 decades without maintenance. The brushes showed wear patterns indicating 32,000 hours of service life before storage, minimal use that explained the generator's exceptional preservation. The cooling system revealed the final piece of the durability puzzle. Modern engines used plastic radiator end tanks and aluminum cores, creating cooling systems that lasted 15 years maximum before requiring replacement. Unit 2487's radiator was all copper construction with brass end tanks, showing minor surface corrosion but zero structural degradation. The radiator could be rebuilt using techniques that any automotive shop understood, unlike modern systems that required complete replacement when damaged. Video footage of Unit 2487's startup spread through railroad enthusiast communities within hours of Chen posting a 30-second clip to YouTube. Within 3 days, the video accumulated 2.4 million views and triggered responses from retired EMD engineers who had worked on the original GP7 production line in LaGrange, Illinois during 1952. Former EMD designer Harold Weinstein, now 89 years old, contacted Chen directly with technical documentation that explained Unit 2487's exceptional preservation. The locomotive had been part of a special production batch built for Southern Pacific's desert operations, incorporating enhanced sealing systems designed specifically for California's extreme temperature variations and dust conditions. The desert package specifications included upgraded gasket materials, additional drainage paths for moisture management, and protective coatings on electrical components, modifications so subtle that standard maintenance manuals never documented them. These enhancements were implemented during a 6-month production window in 1952, affecting fewer than 200 locomotives total. Weinstein's documentation revealed that Southern Pacific's desert-spec GP7s had achieved operational lifespans exceeding 42 years before retirement, compared to 28-year averages for standard production units. The railroad had specifically requested engines capable of operating in 120-degree heat while maintaining full power output, driving EMD's engineers to overspecify every component that might fail under thermal stress. The viral attention attracted railroad museums competing to acquire Unit 2487 for their collections. The Western Pacific Railroad Museum offered $125,000, remarkable for a locomotive that salvage estimates had valued at $8,000 for scrap metal. The Smithsonian Institution's Transportation Division requested permission to document the locomotive for their industrial engineering archives. Yet Chen's employer, Pacific Harbor Line, recognized operational value that museums couldn't match. The short line railroad operated in Los Angeles ports, moving containers and freight cars across trackage where modern locomotives' electronic systems failed regularly from harsh industrial conditions. Unit 2487's mechanical simplicity offered reliability that contemporary engines couldn't provide. The restoration completion demonstrated what modern locomotive rebuilds could never achieve. Total project cost, $47,300 including labor, parts, and paint restoration. Comparable rebuilds of 15-year-old modern locomotives typically exceeded $800,000, while reducing the engine to essentially zero-hour condition that would require another expensive rebuild within 20 years. Unit 2487 entered revenue service on November 18, 2023, hauling container trains through Los Angeles industrial districts alongside modern locomotives costing $2.4 million new. The GP7's fuel consumption measured 22% higher than contemporary units during equivalent operations, the price of mechanical simplicity versus computerized efficiency optimization. Yet the operational cost comparison revealed surprising economics. Modern locomotives required specialized diagnostic equipment, factory-trained technicians, and proprietary replacement parts that only original manufacturers supplied. Unit 2487's maintenance procedures came from a 1952 manual that any competent diesel mechanic could follow, using hand tools and generic replacement components available from industrial suppliers. The locomotive's insurance classification created unexpected financial advantages. Standard Railroad Insurance rated modern locomotives at $180,000 annual premiums, reflecting their high replacement costs and complex failure modes. Unit 2487's mechanical simplicity and proven durability qualified it for $28,000 annual premiums, savings that offset its higher fuel consumption within 8,000 operational hours annually. Railroad industry analysts began publishing studies examining whether first-generation diesel restoration represented viable alternatives to purchasing new locomotives, whose computerized systems created maintenance dependencies that railroads couldn't economically sustain. Standing in Pacific Harbor Line's maintenance facility 18 months after Unit 2487's resurrection, Chen reviewed operational data that contradicted every assumption modern locomotive engineering was built upon. The GP7 had accumulated 14,200 hours of revenue service without mechanical failure, operating at 94% availability rates that modern locomotives rarely achieved, even when new. The engine's performance metrics revealed why EMD's 1952 engineering philosophy had created machines that refused to die. Cylinder wear measurements showed 0.03-inch bore degradation after 18 months of service, acceptable wear that wouldn't require attention for another 30,000 hours. Modern high-performance engines showed equivalent wear within 8,000 operational hours, requiring frequent overhauls that consumed railroad maintenance budgets. The electrical system demonstrated even more remarkable durability. The main generator had experienced 0 failures despite operating continuously in Los Angeles port conditions where salt air, industrial dust, and temperature extremes destroyed modern electronics regularly. Contemporary locomotives averaged 3 electrical failures annually, requiring roadside assistance, delays that cost railroads $3,200 per incident in lost productivity. Unit 2487's maintenance records told the story in stark economic terms. Total maintenance costs for 18 months, $6,800 for routine oil changes, air filter replacement, and standard inspections. Equivalent modern locomotives averaged $34,000 in maintenance expenses during similar service periods, requiring specialized technicians and proprietary diagnostic systems for routine servicing. The GP7's operational success triggered broader industry examination of engineering philosophy. Railroad equipment manufacturers had spent 40 years optimizing designs for initial purchase price rather than life cycle costs, creating locomotives that were cheaper to buy but exponentially more expensive to own and operate. Unit 2487 represented the opposite design philosophy. Expensive to manufacture, built using premium materials and overspecified components, yet capable of operating for generations with minimal maintenance. The locomotive's resurrection had proven that durability and simplicity could deliver better economic returns than efficiency and sophistication. By mid-2025, 3 additional short-line railroads had located stored GP7 locomotives and successfully returned them to service using Chen's documented procedures. Each restoration cost under $60,000 while producing operational locomotives that insurance companies valued at $400,000 based on their proven reliability and low maintenance requirements. The trend alarmed modern locomotive manufacturers, whose business models depended on continuous equipment replacement cycles and proprietary maintenance services. Industry lobbying groups pushed for emissions regulations that would force first-generation diesels off mainline railroads, arguing that older engines contributed disproportionately to air pollution despite representing less than 2% of the active locomotive fleet. Yet the regulatory attempts couldn't erase the fundamental truth that Unit 2487 had revealed. American engineers in 1952 had built diesel locomotives so well that they could sit abandoned for 40 years, then return to service with minimal intervention and operate reliably alongside machines 4 decades more advanced technologically. Chen continues operating Unit 2487 in daily service, its EMD 567 engine running with the same mechanical precision that EMD's wartime-trained engineers designed 73 years earlier. The locomotive that salvage reports declared worthless has become proof that sometimes the old ways were actually the right ways, building machines to last forever rather than planning their obsolescence before they even enter service.